Hello, everybody. I am Ruchika Gupta from the Department of Computer Science and Engineering, Indian Institute of Technology, Guwahati, India. I welcome you all to our presentation on securing on-chip interconnect against delay Trojan using dynamic adaptive caging. This is the flow of my presentation that starts with the introduction to TCMP NanoC, followed by the proposed threat model, suggested mitigation technique, experimental results, and conclusion and future scope. First, let's talk about the paradigm shift from unicore machines to multi-core machines. In unicore system, we have a single resource that is shared among all the applications based on the well-established principle of context switching. While in multi-core machines, we have multiple cores. Each cores are running on dedicated applications, while some of the cores also running the system softwares to provide the environment. Let me walk you through what is the core architecture. The major component of a core architecture is a processor, L1 and L2 cache, a tile controller, and a network adapter. Now the question is how a intercore communication takes place, because it is possible the data that is needed by a particular tile is not present in that tile and that is present on some remote tiles L2 cache. In that case, we need a way such that the tile and the core can communicate with each other. In order to provide intercore communication, there is a router that is connected with each tile, and each router have a interconnected network. Router architecture consists of the buffers, a crossbar that connects input to output, and a control logic to perform certain operations. So now summing up, a tile chip multi-core processor is a class of system on chip that integrates multiple cores on a single tile. And these tiles are interconnected via packet-based network that is known as network on chip. These are few examples of TCMP like Tilera 64, Intel KNL Xeon Phi, AMD Ryzen, or Threadripper, which is a 64 core machine. Now let's talk about that in which format actually the packet flows across NOC. In NOC, the packet is split into a smaller unit called flow control units or flits. There can be three types of flits: head flit, body flit, and tail flit. Head flit consists of all the control field information that is required to travel a flit from source to destination, while body and tail flits contain the data payload. Security of system on chip is a very crucial aspect. All electronic system components are integrated on a single chip where multiple IP blocks are integrated. And that should be integrated in such a way that they become cost effective at the same time that provide better performance. But integration of these third-party IPs also involve untrusted supply chain. That creates a security vulnerability into the system. System on chip design is actually involved. The IP manufacturing is distributed across the globe. Long and globally distributed, this supply chain of hardware IPs makes SoC design increasingly vulnerable to diverse trust and integrity issues. It is possible that IC manufacturing involves the designing and layout and synthesize and fabrication assembly. There are multiple countries are involved across the globe in order to make one IC. This is the potential threat in SoC design that creeps into the system in various phases like specification, design integration, synthesis, and fabrication by designer mistakes, rogue employees, EDA tool vulnerabilities, untrusted vendors, or untrusted foundry. One of such potential threat is hardware Trojan. Hardware Trojan is a malicious circuit that inserted in an IC that alters the system behavior and produces some undesirable consequences. Just consider if we buy, for example, a missile from a country. What if the moment we attack with that missile doesn't work the moment it reaches to a certain GPS? These GPS coordinator acts as a trigger that may activate the malicious circuit that is put inside that IC, and the overall system behavior will be altered. So in this work, we are proposing one of the HT, we call it a delay Trojan, where we consider the HT is present in one of the input buffers of virtual channels, which is creating some delay effect to L1 missed request packets. Even if the link is not congested, it still blocks the control signal and triggers a root computation and triggers the root computation activity that blocks it, and root computation will not take place. After a certain time delay, the control signal will be activated again, but by then it leads to delay in the packet reception. Let me walk you through with the threat model example. Here we are considering 4 is the source, 15 is a destination tile. It needs some data that present on tile number 15. It should go by this route. As the flit moves, we consider 5 is a bad guy. It is the guy where HT is present. Even if the bidirectional link is free, still it will not perform root computation and the flit will remain seated in the buffer itself. After a particular time, the flit will be reached out to the destination. This will cause the unnecessary delay and will degrade the system performance. In order to detect this HT, in order to localize a node that have the HT, and in order to mitigate the impact of this HT, we propose the dynamic adaptive caging module, which consisting of 3 phases. First phase is Trojan detection unit that is responsible for detecting the Trojan. Once the Trojan is detected, caging control unit or CCU is responsible to localize the HT node where HT is present. And finally, to mitigate the HT effect, bypass that HT node by rerouting packets using rerouting unit. This is the phase 1. This algorithm shows how the delay Trojan detection takes place. That works on the principle of delay comparison. What is the average delay till a particular node and compared with the delay in the last node? What is the average delay in the last node and the overall average delay till that node? On that basis, delay comparison will take place. If the delay comparison is more than the threshold, that means after the threshold verification, the alert field activation takes place. Alert flag activation is responsible to inform all the neighbors around HT such that they know that some malicious activity is going on. Now comes upon the HT detection. CCU is responsible for localization. That builds a cage around HT to isolate the HT node. And it informs the neighboring router by sending messenger flit, which consists of the propagation direction, hop count, alert flag, and alert direction. Let me give you an example to understand this. Here we consider node 27 is a HT node, and 26 node gets to know that 27 is performing some malicious activity, and it detects the HT by comparing the delay. It initiates the alert flag known as messenger flits, and it sends it in one clockwise direction and another one is anti-clockwise direction, such that all the router around the HT node gets to know that there is some malicious guy sitting in between. Once the HT is caged, the another challenge is how we can perform the bypassing of that HT node. That is done by the packet rerouting by rerouting unit that explore the alternative path while avoiding the HT node. In this case, all the routers, whether it can be cage corner router or cage edge router, they coordinates for bypassing. Let me walk you through with one example. Here we consider the source is 24 and destination is 6. In that case, ideally it should go like this, but flit instead of that, upon reaching the cage edge router 26, it will bypass the HT node and we'll reach to the destination node 6. Let's take another example where source node is 54 and destination node is 11. The path should be like this, but instead of, it will go to the cage edge router, then cage corner router, and the similar way it reaches to the destination by bypassing the HT node. Now you must be wondering that how we try to capture its result. This is the experimental setup we took into account. We work on 64 tile out of order CPU alpha architecture processors with the relevant L1 and L2 cache configurations. We worked on 8x8 2D mesh topology, while we have taken 0.1 as HT attack probability. SPEC 2006 benchmarks are used for this experimentation. We have categorized the benchmarks on the basis of misses per kilo instruction into high MPKI benchmarks and low MPKI benchmarks. And for different workloads with 5 different combinations, we have tried to collect the statistics. Where WL1 shows the 50 high MPKI benchmarks and 50 low MPKI benchmarks. That means out of all the cores, all the 64 cores, half of the cores are running on high MPKI benchmarks and half of them are running on low MPKI benchmarks. The similar color coding you can see, and it is very well understood that how these benchmarks are distributed. We have taken 3 performance architectures into account to compare and analyze the performance. Baseline or BL is the architecture where we consider there is no HT. DT is the architecture where we consider the presence of an delay Trojan in any of the random routers. And here in this example, in this experimentation, we have taken 27 as a randomly chosen router that has delay Trojan, and DAC where the proposed mitigation technique is used. So we have tried to capture the first results where average packet latency and hops are plotted. Here the x-axis represents all the 3 of the performance architecture, while the y-axis represents the average packet latency in the solid bars, while the checked bars represent the average hops. Here we can say the HT causes the back pressure, and due to the back pressure, all the neighboring routers, that also shows the increased packet latency. But while we use the DAC or the dynamic adaptive caging proposed technique, the packet latency significantly improve, and these significantly improved packet latency can be shown here, where we see that packet latency is as close to baseline. Here we can see the average number of hops are 6, but in the case of rerouting, it reaches to 7.5, though the packet hops are marginally increased, but that is done without affecting packet latency. Another performance statistics we capture is about average miss penalty. This is also, we know that if HT increases the latency, that implies that there will also be increase in miss penalty. But we can see that DAC, that is shown in the red bar, the dynamic adaptive caging, that actually reduces the packet latency, and hence the average miss penalty is also reduced. While we perform the rerouting, we can see the rerouting performance. Also, we can see the impacted packets have very less average packet latency. So somewhere it is very much visible that how DAC is able to restore the system performance. Another statistics when we are trying to find out the average packet latency across all the workloads, and we can see the trend is more or less similar across all the workloads. We can see the missed penalty reduction varies across workloads based on MPKIO benchmarks, and DAC reduces the AMP as well for all the workloads. We have also come up with a heat map analysis to show what is the cumulative buffer count and cumulative flit count. And we can see that cumulative buffer count in the case of DT is showing with the ultra high occupancy, while in DAC, because of the isolation of HT node, it is shown in very small, very light buffer occupancy. The similar trend is also visible in the case of CFC or cumulative flit count. With this, I would like to conclude by saying that we propose the HT attack possibility that incurred delay to selected packets. We call it delay Trojan. And we have tried to analyze the impact of HT qualitatively and quantitatively, both at core level, cache level, and network level. The proposed DT, we assume that present randomly at any NOC router that shown the ability to degrade the overall system performance. But later on, we also see that system performance is restored by suggested threshold statistics-based detection localization technique that we call dynamic adaptive caging, that supports packet rerouting and that bypasses the HT node. So we could able to recover the system performance at minimum cost in terms of average packet latency, average miss penalty, area, and overhead. And definitely working on with a variety of impacted message type, not only L1 miss request packets, for variety of threshold and a variety of workloads will definitely holds the very potential future work scope. Thank you for your patient listening. Thank you so much.